Right, so in 4.3, we looked at rational functions. Okay, those are functions that have fractions. In 4.4, which is the last section for this chapter, we look at radical functions. Okay, so radical functions are basically functions that have a root in it. It could be a square root, it could be a cube root, but it has some kind of root. Okay, there's a couple examples of radical functions. The one on the left is more typical for what we're going to work with, especially when we talk about transformations, which we will today. This minus 2, probably be able to guess, but that is a shift 2 units to the right. Yeah, 2 units to the right. So the transformations with radicals are exactly the same as the transformations we learned with every other function. But I'll make a little diagram and we'll label the A, B, C, D, so we make sure we know which one is which. Okay, so any expression that has something like this in it, okay, it's got this symbol. It could have a number greater than 1 in that spot right there. Like in the case on the right, I have a 3. That number just tells you the kind of root. So any expression that has that symbol could have a number where the n is, and then it'll have something underneath it. That is called a radical expression. So any expression that looks like that is called a radical expression. The n, which has to be an integer greater than 1, so remember integer means no decimals, that's called the index. So the index tells you the kind of root you're taking. If you don't put an index, actually I think I'm going to mention that in a second. Yeah. If you don't put an index, it's always a square root. If you want to write down something other than a square root, you need to put what the index is. And I'm going to show you on the calculator how do you type in like a cube root or a fourth root or something like that. Okay, so n is called the index. A is called the radicand. Okay, the radicand is what's under the root symbol. And that actual thing itself, like the little check mark or the horizontal line, that's called the radical sign. Okay, so any questions on any of those terms? Index, radical, radical sign, radical expression. Radicand. Okay, so a couple things we're going to look at. One thing we're going to look at is the transformation, I already mentioned. Second thing we'll look at is how to type it in like on a calculator and graph. And the third thing will be solving some equations that have square roots or cube roots in them. Everybody have that? Okay. So I just said that, but if there is no index, you always assume that the index is a 2. 2 means square root. Okay, it means square root. Now, there is a way that you can write square root without using that symbol. Okay, you can actually put an exponent, and there's a certain exponent that means square root. Not 2. 2 would mean square. If there's something that means square root, yeah?
Would it be to the half?
Yes. If you raise something to the 1/2 power, that's the same thing as taking a square root. Let's try it. Try with an example. If we take the square root of 16, what should I get? 4. If I take 16 and raise it to the 1/2 power, I get 4. So raising something to the 1/2 power is the same as a square root. What do you think if you wanted to do a cube root? What power do you think would be cube root? Yeah?
1/3.
Yeah, 1/3. So raising to the 1/3 is a cube root. How about a fifth root?
1/5.
That would be a 1/5. So instead of taking the fifth root of x to the 4th, we can raise it to the 1/5. And in the last one, something happens here. When you rewrite it with an exponent, you end up with a power to a power. What do you do when you have a power raised to another power? Something you do with those two exponents.
Multiply.
You multiply them. And what's 4 times 1/5?
4/5.
4/5, yeah. So this last one is one of the reasons why you might take something that has a root symbol and rewrite it with an exponent, because then you can simplify it. In the top two, well, there's really no reason to do what I did there, because nothing simplifies. It's just doing it a different way. But the idea is if you want to do a root, the exponent is 1 over the index. So cube root 1/3, 4th root 1/4. Okay. Any question on what power you can use in place of the root symbol? Yeah.
Why is it that way? Why does it have to be 1 over the root?
Why does so like kind of the proof behind it?
Yeah. In like what terms?
I'd have to think about it a little more. I haven't thought about that in a while. So honestly, off the top of my head, I can't remember the proof of why you can change the square root to a 1/2 power. All we have to know is that you can. But that's a great question, the proof why. I bet if I looked it up, it would come back to me quickly. I just can't think of it off the top of my head.
We just go by that if we have to.
Yeah.
Isn't it because like you can multiply by decimals to do division? Isn't it the same concept?
Well, remember, raising to a 1/2 power doesn't mean multiply.
Well, I know, like the thought that you could raise a fraction to root would be the same as you can multiply by a fraction to divide.
To divide, yeah, it might have something to do with it. I'd have to kind of see the reason. Because usually when we do exponents, when you do like integers, it makes sense. Right? When you take x and raise it to the 5th power, it means to take the base and multiply it by itself 5 times. Well, how do you multiply something by itself 4/5 of a time? You can't really extend that same thinking with integers to when you get into fractions.
Is it not just itself times 4/5 of itself?
No, it would be like, if you want to think of it that way, it would be like multiplying x times itself 4/5 of a time.
Oh.
Yeah. Like if this was squared, you would just say multiply x by itself 2 times. If it was cubed, x times itself 3 times. This is x times itself 4/5 of a time. So the thinking doesn't quite extend to fractions in the same way. So we'd have to look up a different reason why it works. That's a great question. I will look it up and let you know. Okay, so what does it mean? Yeah?
Just like a kind of in the same way of thinking. If you took like the half root of something, would that square it?
I don't know if there's such a thing as a half root. Roots are usually defined to just be integers, like square root, cube root, 4th root, 5th root. There's no such thing as decimal roots, like the 1.5 root or the 0.5 root. It's an interesting thought, but I've never seen roots defined with decimals like that. Yeah. Okay, so when you take a root, okay, let's, for example, think of a square root. What's the square root of 9? 3. Yeah?
Just to follow what Carlos just said, according to the calculator, the half root of 2 is 4. So a half root would be the same as raising
the half root?
Yeah.
Okay. Yeah, so it's a very interesting idea. I've never really thought about it too much, but it kind of makes sense if you think about it the way I showed you. You're kind of thinking about it the reverse way. Yeah.
Wait, so if you're doing like the half root, would it be x equals x times whatever half of x is?
Technically.
And is that how you
I don't know. I have to think about it. I've never really thought about fractional roots. Yeah. I'll look it up after though, and I'll see. So, yeah, I asked you, when you take the square root of 9, you get 3, but you also get something else. Negative 3. There's always 2 answers. But when they ask for the principal root, they want 1 answer. Okay, so principal root means 1 answer. And if it's odd, what you're basically doing is solving this equation. So this is how I would explain to somebody what a root is. If they didn't understand, like if let's say I said find the cube root of 64, and someone said I don't understand what a cube root means, I would say, well, it means that there is a number you can raise to the 3rd power and get 64 as the answer. That's how I would explain a cube root. There's a number you can multiply by itself 3 times and get 64. So if you can solve this, then what you're really doing is a cube root. And what is the answer? What number do you raise to the 3rd power? 4. Yeah, 4 to the 3rd power is 64. Now with odd roots, there is no restriction on this number. You can take the cube root of an odd number, positive number. You can do a negative number. You can do 0, fractions, or decimals. Right? Let's try a negative. So to do a cube root, press math, and then you can do option 4. So that's a cube root. And if I put in a negative number for the cube root, no problem at all. So when you're dealing with an odd root, the radicand can be anything you want. Anything. Math and then option 4. Now, how about when we deal with even index roots? When we deal with even roots, like a square root, can I take the square root of anything that I want? No. Yeah, it has to be, well, it has to be, it can't be negative. You know, when I say that, you know the difference between saying it has to be positive and it can't. It can be 0. Yeah. So if you try to take the square root of a negative, we're going to run into a problem. It's going to say it's imaginary. So whenever we deal with roots that are even, not just square roots, 4th root, 6th root, 8th root, any even root, whatever you put under the symbol for the radicand has to be 0 or higher. That's only for even roots. And the answer that we are looking for is not negative. Okay, we're always looking for an answer that's 0 or higher. So if I wrote this, and I said to you, find the principal root. All right, say, okay, that's a square root, so that's even. Let me make sure the number underneath the root is greater than or equal to 0. Yep, it's 16, so I can do it. So I want the answer to this problem, and I don't want you to tell me the negative answer. So what's the square root of 16? Just 4. Right? I'm just looking for the non-negative answer. The way you'd know if I'm looking for the positive and the negative is you would see that symbol in front. When you see a plus or minus in front of the root in the quadratic formula, then you know I want both. Okay. Otherwise, just the positive answer. Question on that? And again, if you don't quite understand what does it mean to take the square root of 16, it means that there's some number you can raise to the 2nd power and get 16 as the answer. We're solving that equation. If you can figure out the answer to this problem, then you know how to do a square root. All right, so let's take a look at this. We're going to figure out when we take a square root, if it gets smaller or it gets larger. And you see what I did with the font there? smaller, it's smaller, but then larger, it's larger. It's like a vertical stretch of smaller. All right. So let's look at some of these numbers and take the square roots. Let's start with 4. What's the square root of 4? 2. So when we took the square root, did it get smaller or larger? Okay, so taking a square root in that case made it smaller. Let's do 18. Okay, square root of 18. Oops, not the square root of the square root. 4.2. That's smaller or larger?
Smaller.
Okay, so based on those two numbers, you might think, okay, when you take the square root, it always gets smaller. Well, let's try 1. What's the square root of 1? 1. Okay, well, based on that, maybe you say when you take a square root, it always gets smaller or stays the same. All right, let's try 0.5. Okay, square root of 0.5. 0.71. What happened that time? It got larger. So the answer to the question whether the square root makes a number smaller or larger, it depends. Depends. It can get smaller, it can get larger, or it can stay the same. There's only 2 numbers you can take the square root of and it stays the same. 1 is one of them. Yeah.
Is it just that like decimals, the square root is larger, and then whole numbers, the square root is smaller?
Well, decimals between 0 and 1 will get larger.
Okay.
A decimal like 1.6, if you take the square root of that will still get smaller.
Okay.
So it really has to do whether the number is between 0 and 1 or bigger than 1. If it's exactly 0 or exactly 1, it stays the same. Square root of 0 is also 0. So what do you think would happen here? 0.2. Yeah, that would get bigger because it is between 0 and 1. So take the square root of 0.2 and you get about 0.45. All right, so what we're going to do now is let's graph some roots. Let's do a square root and a 4th root. Okay, so I can show you how to type in 4th roots. All right, well, square root, you got a button for it. Just second, and then press x squared. So there's a square root. Now, the way you do any root that's higher than a 3, you start by putting in the index. So we want to take a 4th root, so put in a 4. Press math, and then press 5, the 5th option down. If you do that, it'll turn the 4 that you put in first into the index. It should look just like that now.
I mean, you could just do the math 5 and then
Math 5.
And then you put the numbers after.
Yeah, maybe you could do it after. So if you do math 5, yeah, then you can put in the number after. So either way, you got to put the number in before, you got to put the number in after. It's pretty much the same amount of buttons you have to press.
Is it okay for those to do F25, F26, I mean?
There might be different options. Yeah, that's a shortcut, I guess. I don't know how much of a shortcut it
It's kind of the
is.
same amount of buttons.
Yeah, it's kind of the same amount of buttons you'd have to press.
How do you get to that one?
It's alpha F2, but it's really the same as just pressing math 5. You still have to press 2 buttons to get to it. Okay, so let's do the square root, the 4th root, and then let's do zoom 6. Okay, so there's your square root. And there's your 4th root. Okay. First thing is, where are the graphs?
In the upper right quadrant.
Right, they're in the upper right quadrant. Okay, so we don't really need to look at quadrants 2, 3, and 4. So then let's just focus on quadrant 1. Okay, so I'm going to zoom in a little bit. So let's set that to 0. We can keep the x max at 10. That's fine. I don't think I need the y max to 10. Not in that case. I could probably get away with 5 because it doesn't go off the screen. Okay, Here's a little bit more zoomed in look. I think you can see something a little bit better. Good enough. Okay, there's 2 points that these graphs cross each other. Does anybody see the first point where they cross? Yep.
First one is like 1, it looks like.
Yeah, they do cross each other at 1, 1. And that's because if you take the square root of 1, you get 1. If you take the fourth root of 1, you get 1. It's the same answer. And there's one more place they cross, yeah.
0?
Yeah.
Go to origin.
They cross right there. 0, 0, and 1, 1 are common to all even root graphs. Now, if you say, well, what if you took this and you shifted it up or down? Well, now you've changed it. I'm talking about if you don't shift it up and down or left and right, you just graph it the way it is. All even roots will go through 0, 0, and 1, 1. And they switch places at 1, 1. Whichever one was below, after the number 1, it becomes above. Whichever one was above becomes below. They switch. How about the domain? If these were only in the first quadrant, what's the domain?
From 0 to positive infinity.
0 to positive infinity. Yep. Including 0. How about the range? What's the lowest that those graphs go?
0.
And the highest?
Infinity.
Infinity. Yep. So that's exactly what we just said. The domain and range are 0 to infinity. And 0, 0, and 1, 1 are common to all even root graphs. If you don't shift it up and down or shift it left and right.
So all parent.
Yeah, like all parent functions, yeah. Yeah. So I'll let you copy that, and then we're going to do the same thing with quadrants. We'll graph we'll graph like a cube root and a fifth root. And when we graph odd roots, I kind of want to do the same thing. Are there any points that are common to all of them? What's the domain? It's the range. So there's all right, I'm going to clear that because I want to change it to a cube root. So mat option 5. And I want to do a fifth root. Since I already have the fourth root typed in, I can just highlight the 4 and now make it a 5. You could add the 7th root, then the more you add, it starts to get confusing. So I just want to do a cube root and a fifth root. I'm going to reset my window though. I want to go back to Zoom 6. What's one thing you notice that's really different right away with a cube root?
It's an S.
Okay. Can you be a little more mathematical?
It's a parabola that's twisted.
Okay. How about in terms of the direction it goes? Yeah, it goes all the way to the left and to the right. So even roots only go in one direction. The normal direction for an even root is to the right. If you mirror image it, it could go to the left, but the normal direction is right. Odd roots go in both directions. Let's zoom in a little bit. Maybe let's go like -3 to 3 on the y and see what else we can look at. I want to see if there's any points that look like they are in common. Now it should look connected. It might look like there's a gap there. It shouldn't be. It's just because it gets steep, and we know when the calculator tries to draw something steep, it kind of gives up. All right, let's look at this one. Might be a little harder to see, but are there any points that look like where these graphs cross? Yep.
-1, -1.
So -1, -1. There's a point right there. So that's one place they cross, yeah?
0, 0.
0, 0. They do both go through the origin.
1, 1.
And 1, 1. So without any shifting or stretching, those 3 points are common to every odd root graph. What's the domain of the blue and the red graph? All real numbers. I told you when you do cube roots or fifth roots, you can take the cube root of anything you want. It's all real numbers. How about the range? It's also all real numbers. It's going to go up forever, and it goes down forever. So here's the same type of information we did for even roots, except with odd roots. 3 points they all have in common. Domain and range, all real numbers. Now, if you shift it left, right, up, down, or you stretch it, will this domain or range ever change? No. How come?
It's still going.
Yeah. If something goes forever left and right and you shift it right 3 units, well, it still goes forever left and right. So there is no changing the domain and range of an odd index root. You can't. Even, yes, you can. Okay, so that's kind of the first thing with roots, just looking at what they look like. And now we kind of know what we're looking for. When I'm asking for an odd root, I'm going to look for a picture like that. Even root looks more like that. And this point, I'm going to refer to that point right in the middle as the center point. I call this point the start point. So odd roots have a center, even roots have a start. Yes?
So for the number 1 and the common to all graphs, those points are only when it's not translated.
Correct. Yes. If you translate these left, right, up, and down, you'll still have 3 points in common,
Yes.
but they might all be different.
Okay.
Yeah. And that's important to know, because I might ask you on the test, when you look at this graph, does it have a start point or a center point? If it's an odd root, it's a center. If it's an even root, it's a start. We're going to talk more about how do you find where it starts, because when we do a sketch, that's one thing you need to know. Where do you start drawing it from? Either the start or the center. How do you graph it? All right, so let's talk about the transformations.
Can you go back for a second?
I'm going to do the transformations down here because I have more space. Okay. So each one of those letters does one thing. 2 of them are shifts, 2 of them are stretches, 2 of them are backwards, 2 of them are not backwards. All right, let's start with the A. The A is inside the root, and it's addition. Does anyone remember what the A usually does? It's inside and it's addition. So it's a
Horizontal shift.
it's a horizontal shift. And it is backwards. So if you do minus, it's going to move it to the right. And if you do a plus, left. Okay. How about B? It's still inside, so it's going to have something in common with A, but it's multiplication, it's not addition.
Horizontal stretch.
That's still horizontal, but it is a stretch. And remember, that is backwards too. So if you put in a really big number, like let's say you put in 10 for B, a big number compresses the graph smaller. So if you put in, like, say you had this, I would say that's a horizontal compression by a factor of 10.
Which way is
Or you
A?
could say shrink.
Which way does A move left?
If A is positive, it would move it left. Negative would move it right. So I would say this is a compression by a factor of 10. Now, if you put in a small number makes it bigger. So I would say this is a stretch by 2. That's how you read that one. 1/2 would stretch the graph twice as much. 1/3 would stretch it 3 times as much. 1/7, 7 times as much. The smaller you make the fraction, the bigger and bigger it stretches it. Okay, so B is backwards. How about C? Now we're multiplication, but we're on the outside. So that's going to be,
Vertical stretch.
yep, it's a vertical stretch. And that one is not backwards. If C is a big number, it stretches it bigger. If C is a small number, it makes it smaller. And what about D? It's addition, like A, but it's on the outside. That's your vertical shift. And it's not backwards. So positive for D would move it up, and negative would move it down. What if the B or the C was a negative? You had something like negative square root. Yeah.
If C is negative, then that would be a reflection of the x-axis.
So yeah, if C is negative, that's a vertical reflection, which is over the x. And if B is negative,
It would be a reflection over the y-axis.
that's a horizontal reflection over the y. Yep. So the A, B, C, and D, it's exactly the same as every A, B, C, and D I've written for every function all year.
Which numbers is it that inverts it over the axes?
So B could cause a horizontal reflection if it was negative. And I need to erase this. C could cause a vertical reflection. Thank you. Yep. If it was negative.
For D is positive up.
Yes. Positive is up and negative is down. Anyone want me to write that? Positive up, negative down? Okay, so there's really 6 things that could happen. If you had all of them, you could have 2 shifts, 2 stretches, 2 reflections. That's six things. But you're not going to have one that's that complicated. I'm going to give you, something kind of like that. And it says explain how to sketch this graph based off that one. Okay. So first of all, in g of x, how many transformations are happening?
One.
Just one. When you name them, you have to do them in order. And the order is the letters that I use. Start with A, then B, then C, then D. If you're missing one, you skip it. So that -2, what letter is that?
A.
That's like your A. And it's a minus. So what's that -2 going to do? It's going to shift right to. And that's it. That's the only transformation in that one. Okay. How about h of x? How many transformations there? Yeah, just one again. And that +3, it's in the same position as the last one. So that's like your A, but it's a +3. So that's going to do what? Yep.
Shift left 3.
It's going to shift left 3. Okay, so that's h of x. And the last one is k of x. But what's wrong with the radicand? It's what?
The 3's before that.
Right, we don't like to put the number before the letter. We usually write it so that the number is after the letter. So let's fix that first. So how could we rewrite that? Right, that's really -x + 3. And how many transformations do we have? 2. Well, the first one's the same as the last one. You're shifting left 3. So we'll keep that one. And now that negative, that's in the B spot. So what's the negative? What's that going to do?
It's a horizontal reflection.
That's a horizontal reflection. And if you're not sure what horizontal reflection means, it means this. It's like a left to right flip. So you could also say over the y-axis. So any questions on describing the transformations?
What would be the difference between if instead of x was just negative x, what if it was like negative 4x? What would be the
Well, then there'd be 3 transformations if you had that.
okay.
So I would still say a shift left 3. I'd still say the horizontal reflection, but then I would say compression horizontally by a factor of 4.
Okay.
So I'd have to add that one in. And where you say the horizontal compression, you can say it before the reflection or after the reflection. But it has to be immediately before or immediately after. Okay? Horizontal reflection has to be right next to a horizontal stretch. Same thing with vertical. If you have a vertical reflection, it has to be right next to the vertical stretch. Could be before it or after. It's got to be right next to it. Okay. Any other questions on that? Okay. So now that's the transformation. So the second thing we're going to look at now is how do we do a sketch by hand. So the first thing you need to know if you're going to sketch it is if it's an even root, you need to know the start point. Where do you start from? If it's an odd root, you need to know the center point. Well, if you don't do any shifting or stretching, the start point is always 0, 0, so is the center point. But we're going to do shifting and stretching. So where is this point going to move? That's what we need to figure out. How does it move? Well, this point has 2 parts to it. It has an x value and it has a y value. And we need to find each one separate. To find the new x value of your start or your center, depends if you're doing even or odd numbers. Let's use it. Set the radicand equal to 0 and solve it. So to find the x value of your start or center point, set the radicand equal to 0 and solve. This might have something like this. That's an even root. So would that have a start or a center?
Start.
That has a start. If I wanted to find the x value of the start, it's not going to be 0 anymore because I've shifted it. Set that equal to 0 and solve. That'll tell you where the x value goes. Now, once you know the x value, let's say the x value came out to 4. All you have to do is take 4, plug it back in for x, and then you have the y value. So take your x value, substitute it back in, and your formula will give you the y value. Now that only gives you one point. Okay, that gives you like the start point or the center point. So let's say you have that point. If this was a start point, you still need at least 3 or 4 more points. I would say maybe one like that, and then like that. Then you could draw your sketch. So you're still going to need about 3 more points. We're going to use the table to get it.
So the 3x plus 2, you replace that whole thing with 0?
Well, you set it equal to 0.
Oh, okay, I see.
Yeah, so the 3x plus 2 is the radicand. You would set it equal to 0 and then solve it. Now, if that was a center point, because we were doing an odd root, I would say try to get maybe 3 or 4 points on one side. You know, maybe something like that. And then 3 or 4 points on the other side. So you need about, I'd say 4 points to do an even root, and then 7 or 8 points for an odd root, because it goes left and right. That's what I just told you. So once you get your start or your center, check some points on each side if it's a center. If it's a start, you only check points on one side. So remember, a start point doesn't go in both directions. And if your graph is supposed to curve to the right, and you try to check x values that are to the left, where your graph doesn't go, you're going to get imaginary answers. So you have to make sure you check points in the direction your graph is actually going to be drawn, not the way it's not. Oh, actually, is that similar to the one I wrote down? Oh, a little bit. Okay, so before I even plug anything in, I just want to know, when I graph it, am I looking for a start point or a center point first? I'm looking for a center. That means I got to check points on each side of it when I'm done. Okay, to find the center, it's not going to be 0, 0, because I've shifted it. How do I get the x value?
You set the radicand to 0.
Set the radicand to 0. So set 3 minus 2x equal to 0. You're going to get 3 equals 2x. And then how would you get x by itself? Divide by 2. That's the x value of where the center point is, 1.5. So 1.5, comma. Now I need the y value. To get the y value, you just plug the number back in for x and see what you get. So we're going to plug in 1.5. What's 2 times 1.5? 3. And what's 3 minus 3?
0.
We already knew that was going to happen. If we didn't get 0 when you plug that number back in, then you didn't get the right number. So 0. What's the cube root of 0?
0.
0. And then times 2.
0.
Still 0. Plus 1. 1. That's really the only number that affects the y value of the center. It's the number that you add or subtract outside the root. Everything else is a 0. So that's your center. Okay, any question on how we got the center? All right, so now we need a graph. Let's put that there. We can graph the center. So 1.5, 1. And I need to plug in some x values into this formula that are bigger than 1.5, maybe 3 of them, and then smaller than 1.5, 3 or 4 of them. But I don't want to put them, I don't want to do that by hand. So what would make it faster to get a table of values? And I don't have to do it by hand this way. How could I get some values quicker than plugging them in by hand? Yeah.
The table.
Yeah, use the table on the graphic calculator. Okay, so type in your root. So 2 times the cube root of 3 minus 2x. 3 minus 2x. And then plus 1. Make sure you put the plus 1 outside the root. Okay, now what I like to check first is let's check the center and make sure 1.5 comma 1 is a point. So I put 1.5. Perfect. That's exactly what I got for the center. Now let's pick some x values that are bigger than 1.5. Try to space them out a little, but don't go beyond 10 or negative 10 because my graph paper doesn't go beyond that. So what would be some x values bigger than 1.5? Yep.
3.5.
Okay, we can do 3.5. What's another one?
5.
5, and let's move over a little to get one at 9. Okay, now how about smaller than 1.5?
0.
Yeah, we could do 0. That's a good one.
Negative 10.
Negative 10, I'll do one right in the middle. Negative 5. Okay, so we're going to graph those points.
How do you get to the table again?
Second, and then graph.
Alright, thanks.
Okay, so we got 3.5, negative 2.1. 3.5, 1, 2, 3.5, negative 2.1. Maybe about right there. What else? 5, negative 2.8. So 1, 2, 3, 4, 5, negative 2.8. And then we've got 10, 9, about negative 4. About right there. So there's the curve on the right. Now let's do the left. 0, 3.8. Negative 10, a little above 6.5. And negative 5, just below 6. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6. Oh, like that. Yeah, that's pretty good. And now just connect your graph. And there's your sketch. Right, we can compare it to what it should look like. Zoom 6 might be a little bit steeper in the middle than I drew it, but I think we still got a pretty decent sketch. And it should not be in two pieces. Remember, these graphs are always connected. It's just the calculator can't do it that way.
Are there calculators that can?
Possibly, yeah. There might be some calculators that can do it. I would bet there are. It just must be the kind of programming that's in this calculator because it gets almost vertical. If you zoom in there, it might actually look connected, or it might look worse. I don't know. Let's see. So if you zoom in near that middle spot, yeah, it starts to get too steep right in the middle.
Can it not draw vertical lines?
It can't draw vertical lines when you do y equals notation. We can draw vertical lines in a different notation, but we'll save that for later. But yeah, y equals, it can't do it. That's another reason why if you try to draw a circle on the calculator, it actually starts to look more like this. Because these two parts on the side, they get too steep for it to connect it. If you try to do it in y equals. There's another way we can do circles and they look perfect. But we'll save that for later as well. Yeah.
Why does it not matter about horizontal lines?
Because horizontal lines are functions. They pass the vertical line test.
Oh.
So the calculator can't draw things that fail the vertical line test. Technically. I can kind of draw a circle by cheating and drawing like the top half and the bottom half separate. But it's not really a circle. Just two halves. Okay, is there any question on that one? All right, let's see what else we got. That's it. How about this one? I'm not going to go through it completely. I just want to ask you a couple questions. Would it have a start or a center? It would have a start. Now, which way do even roots normally curve?
To the right.
They normally curve to the right. Think of that radicand like this. What's that negative going to do? That's a horizontal reflection. So if something used to curve to the right, now it's going to curve to the left. That's the idea of what this one's going to look like. It's going to curve left. So once you get your start point, are you going to pick x values bigger or smaller?
Smaller.
You have to go smaller this time because it's going to curve to the left. And you'll know when you go to your table, if you go the wrong way, you're going to start getting imaginary answers because there's no graph over here. Right? Any question on the idea with that one? You set the radicand equal to 0. You solve it. Plug it back in. and then get your y value, and then go from there. All right, so that's really the second big thing for today. So we looked at the transformations, we looked at how to do sketches, and this is the last thing. So how do we solve an equation that has a radical? To solve an equation that has a radical in it, the first step is to get the radical alone. Here's an example of an equation that has the radical isolated on one side. In that equation, the radical is by itself on the left side. Here's an example where it is not isolated. In the one on the right, there's something on the outside of the radical. So if you were going to solve this one on the right, the first thing you have to do is get rid of this 5. How would you move this times 5 to the other side? Yeah, you divide each side by 5. And then you'd have the square root of x minus 3 equals 12/5. And then you go from there. Okay, but that's always the first step. Get the square root by itself on one side, or cube root, whatever the root is. And then to cancel a root, you raise to a power. If it's a square root, you square. If it's a cube root, you cube. And that's usually the highest ones that we're going to do. We do have to check for extraneous solutions. So when we dealt with rational functions, that means you would plug it back in and it would cause you to divide by 0. Well, in this case, we're going to plug it back in and just make sure that it works. If it doesn't work, we need to cross it out and write that it was extraneous. It did not work. That's pretty much it. We'll just try a few examples. I think I'm going to switch example 1 though. Nope, actually I'm not. We're going to do that one. Example 4. Okay, so first thing, is the root by itself on one side in that problem? Yeah. There's nothing on the outside of the root. You can have as much stuff as you want inside. I just don't want to see something like this. I don't want to see numbers on the outside of the root. All right, so the root is already isolated, and it's a cube root. How do you undo a cube root? Can you say it again without saying the words add, subtract, times, or divide? Raise it to the third power, yeah. So you're going to raise each side to the third power. Okay, and the same thing here. Okay. What happens on the left when you cube a cube root? Okay. Yeah, the radical is gone. You still have the radicand. Okay, we still have that. Squared minus 2x plus 2 equals x cubed. And when we try to solve something that has higher exponents, like 2s and 3s, what do we always try to get it equal to?
0.
Right. We always want to get it equal to 0, and then hope that we can do something. I would move everything to the right. You might think, well, that's more to have to move. But I would keep this x cubed positive because of about what we're going to do next. Okay, so we're going to have the x cubed on the right. How would you move the x squared? Subtract it. How would you move the negative 2x? Add it. And how would you move the plus 2? Subtract. What's one technique that we use? We do it a lot with quadratics. when we try to solve them. If the numbers work out nice, we can do this. Yep.
Factor by grouping.
Yeah, we can try to factor it. And this has to be doable by factor by grouping, or we're not going to be able to solve it. Okay. So, Brady, if you factor what you can out of the first two, what do they have in common?
X squared.
Yep. And what does that leave you with?
X minus 1.
Right. So the goal now is to get x minus 1 again when we factor. Okay. What can we factor out of the second thing that I just put a bracket around? We can factor out a 2. And what would that leave you with? That also leaves you with x minus 1. That's perfect. That's what we needed to happen. Okay, now, what do that and that have in common? So now we're going to take out the x minus 1. If you take the x minus 1 out from the first one, what's left? Just x squared. And if you take x minus 1 out from the second one, what's left? Just a plus 2. So now we factored it. What do we do with each one of these factors? Set them to 0. So either the first factor is going to be 0, or the second factor is going to be 0. Okay, when you solve the first one, what do you get for x?
Negative or positive 1.
Positive 1. We'll check that, but as long as it works, that could be the answer. What's your first step to get x by itself here?
Subtract 2 from both sides.
You'd subtract 2 from both sides. But what's going to happen if you keep continuing with that?
You're going to get the square root of negative.
You're going to get the square root of a negative. So from this part, there's no solution. It doesn't mean the whole problem has no solution. It just means there's no answer from this part. So the only answer we got was 1. Okay, let's check it. If we plug in 1, what's 1 squared? 1. What's 2 times 1? 2. And then plus 2. What's 1 minus 2 plus 2?
1.
So we get a 1. What's the cube root of 1? 1. And what's 1? Well, we would just have 1 on the other side. So we get 1 equals 1, which means it worked. 1 equals 1. And that's it. That's your answer. Any question on that? Yeah.
So even though that answer would be imaginary, could you still use it to solve it? Like if you plugged in I squared would be -1 minus plus.
Would it work for imaginaries? I'd have to check and see. It might work. Yeah, I'd have to do it all out and check it, but yeah, it might work. But you don't have to worry about the imaginary in this section. But that is a good question. I would never really thought about taking like cube roots with imaginary numbers. Thought about doing that. I have to. Another good question I will look up, and I'll let you know. I'm going to change that one. Let's try this one. Okay, so it's just solve algebraically. Square root of x minus 3. And since I'm just making this up, there is a chance it comes out to no solution. Square root of x minus 3 equals x plus 1. Okay, so first thing, is the root by itself on one side?
Yes.
Yes, it is. So what would I do on each side to get rid of that root? Raise it to the power of 2. When you square the square root, that's gone. You have to be careful when you square x plus 1. That's not just x squared and then plus 1 squared. That's FOIL. So you have to think of it like this. That's what you have to do on the right side. X plus 1 times x plus 1. And what's that going to come out to?
X squared plus 2x plus 1.
I told you we could get a no solution. So that's a quadratic because the highest exponent is a 2. And what do we have to get it equal to?
0.
We'll get it equal to 0. So to get it equal to 0, I want to move the x to the other side. And how would I move the 3 to the other side?
Add 3.
So what do we get on the right?
X squared plus x plus 4.
Yeah, we get x squared plus x plus 4. And that's not factorable, so you could try quadratic formula. What are your a, b, and c?
1, 1, 4.
Yeah, 1, 1, and 4. When a and b are that small and c is a big number, that's not good. That means you're going to probably get an imaginary answer. So that's why I was kind of looking at it. I knew right away when we did the first step, it wasn't going to work. So negative b plus or minus the square root, you got b squared minus 4 times a times c. Well, 4 times a times c, I can pretty much stop there because that's 1 minus 16. Okay, that's going to be a negative. So we didn't do anything wrong. And if it did work, well, we would just simplify what's under the square root and we'd be done. But in this case, there's no solution. Had I made this a plus 3 right here, then the whole problem would have worked fine. But I didn't. So. Any question on?
So no solution.
Yeah, there's no solution here. Okay, so let me put up the homework. Yeah, I am gonna change it slightly.
Stop doing it. This happens every time. Stop. Wait for him to change it, bastard.
Really bigger than you.
Still calling me bastards. Never stop. Never stop. Never stop. Kind of bad, honestly. I call everything. I call it intimate objects. It's not good.
Okay, that's it. So it's 255, and it's I think it's 10 questions. 5, 6, 12, 14, 20 to 22, and 31 and 35.